Okay, so there was a lot of interest in the de holography stuff afterwards, and I promised some references. So here's a sequence of them. I did want to say that the positive thing about the DSCFT is that it, as opposed to the derived thing from uplifting, is that it preserves more of the symmetry, so it uses the space-like slice and preserves symmetries in that way, which made it kind of a nice tool for organizing some aspects even of the kind of cosmological perturbations that you've been hearing about from Leonardo. And so just for that reason, it's been a nice story. Maybe we should give people a few more minutes. So, it's one of those things where you can take it at sort of different levels. There's a weak version, which is just, okay, de Sitter has a certain symmetry structure. And that has been something that people use to, for example, constrain the shape of the non-Gaussianity of the tensor modes, for example, and things like that. So it's definitely useful at that level. When it comes to postulating a full-fledged CFT dual description, it gets much harder, I think. So I think that's a fair summary. Are there any more questions about that? Because I'm going to come back now to the main subject, which is inflationary cosmology and its intersection with string theory. So, okay. So, well, we spent a fair amount of time on the potential V. The next thing we need, and this is going to be more interesting than it sounds, is the structure of the kinetic terms for these various scalar fields that we've been talking about. So let me start with the runaway directions, these things where at best we get a kind of three-term stabilization. Just for the record, the canonically normalized field is exponentially related to, in the case of the dilaton, to the string coupling. So this is the canonically normalized field. And a similar thing is true for the overall size of the space. So up to some coefficient, some order 1 constant, the canonically normalized scalar field associated with the size of the extra dimensions is this guy, sigma in the exponent. And the way to see that quickly, if it's not familiar, is to simply compute it from the higher dimensional Einstein term. So have these be our 4 dimensions, the second part of the metric be the extra dimensions, and then compute the curvature, the scalar curvature, keeping track of this mode, and I've already written it as an exponential, and we'll shortly see why. So depending on the dimensionality of the extra dimensions, which I've taken to be k here, sorry, this is getting small. The point is that the kinetic term for the volume is determined from the higher dimensional Einstein term, which in turn depends in this way on the field sigma, which is, as you can see, this thing is the size L squared of the space. Okay, so that's those types of fields. The kinetic terms for the axions are really interesting and important, and so I'll dwell on that for a little bit. First, just reminding you again what these axion fields are. So if I take x as my 4-dimensional coordinates and have some basis of cohomology elements in the internal dimensions, then this NS2 form potential field big B has some low-lying degrees of freedom that are captured by these scalars multiplying such internal cohomology elements. Plus, of course, all sorts of other degrees of freedom, basically KK modes that are massive. And these fields are massless. You can just use the fact that this omega is a cohomology element to show that when you reduce the action to 4 dimensions, these little scalar b's come out massless. But since it's a non-trivial cohomology element, omega is not d of something globally well-defined, it means that it's not pure gauge. So this is a physical mode. This is simply a glorified version of a Wilson line. So where you'd have a similar statement, just say we have a circle and a gauge potential A. I can write the same thing in a very simple way, where my omega is d theta. And of course, on a circle, theta runs from 0 to 2 pi. It doesn't come back to itself, so it's not globally well-defined. So this is not d of anything. And that's the familiar Wilson line. So coming back to the B field in string theory, it's a very basic thing because, again, B is the thing that is sourced by the fundamental string, F1, so to speak. And so if you think about the world sheet path integral, it has this structure. Let's work in Euclidean space. All integrated. So it has the familiar metric term plus this. This is how the B field couples on the world sheet. And as you can see, it's basically like a Wilson line. It's an e to the integral of B. Now this term, if B were constant, this would be a total derivative. So it only gets contributions from non-trivial topologies. And while we're on the subject, let me just say, so again, this is the world sheet string path integral. Integrating over the embedding coordinates of the string. If you have any questions about this, let me know. I assume people have seen a lot of string theory probably in this crowd. So another thing we can see from this is that, so again, what this is saying is that for closed strings, and I've included no Ramon couplings. The constant, there's no dependence on B at this level. But if you look at non-perturbative effects on the string world sheet, so so-called world sheet instantons, where the string world sheet is mapped into some non-trivial cycle sigma in the extra dimensions, or in the space-time. In particular, in the compactification that we're interested in, these things can generate contributions to the effective theory that go like a kind of stringy but classical version of an instanton effect, where you get in our language of the scalar field axion little b, such effects go like e to the IB from this term here, and which can get a contribution from a topologically non-trivial embedding of the string into the space-time, with a coefficient that from this term goes like e to the minus area. So these are so-called world sheet instantons. So this is sort of how people thought about axions for a while in string theory, partly because there was a almost complete focus on the heterotic theory, where there aren't open strings or Ramon fields, and also kind of an analogy to traditional field theoretic axions, which have a similar property that classically there's a exact shift symmetry, and then instanton effects produce an interesting periodic potential. Okay, but as we've already seen in string theory, that once you have Ramon fields, or if you have boundaries, so I should have said here also no D-branes. Once you have these elements, as we've seen, you have a more direct dependence of the effective action on B. Okay, so that's the essence of what is called Axion monodromy as a mechanism for inflation. But I said the first thing I want to do is, having reminded you of what these fields are in 4 dimensions, I want to be careful about I want to compute their kinetic terms, because that's also quite important in this thing. So the Axion kinetic terms come from if I do specifically this B field axion, just as an example, come from the kinetic term for it from the higher dimensional point of view. It's field strength h3 squared. And plugging in that expansion that we had up there, the kinetic term generally takes the form, if we have, say, as you generically would, some number of axions indexed by I from the 2 cycles omega I, the kinetic term would be computed by this integral. Okay, so geometrically, this is what you would do, and one can do it in a wide variety of interesting cases. Just to be clear, and again, please ask me any questions as we go. Why don't I explain it to you in the simplest situation? So, for example, in a single scale product space, for example, here's how this works out. So you have this kinetic term that we're interested in reducing down to 4 dimensions. And so we have, I'll just call it volume. So, the volume is L to the D minus 4 in my units, everything in string units. Okay, so we reduce, and we get a factor of the volume in such a simple space divided by g squared that we inherit from the higher dimensions. We've got the b dot squared, and we have a factor of 1 over L to the 4th from if you like, from the inverse metric factors in this contraction. So just to spell it out, we have H0, M1, M2. The G00 comes down to 4 dimensions, but the others are the things that give these powers of 1 over L. So these inverse metric factors are giving the 1 over L to the 4th. See. Okay, so this is going to become interesting momentarily because here's how we can organize this. So first of all, this factor is familiar also from the dimensional reduction of the Einstein term, and it gives the value of the four-dimensional Planck mass squared. So we can write this as, in 4 dimensions, just m Planck squared over L to the 4th b dot squared. Okay, so this is traditionally called, I mean, this factor is traditionally called just f squared for reasons we'll see shortly. But we also want to, okay, so just as a notational thing, let's insert that notation, but we also want to connect it to the canonical field, which I'll call phi. Okay, so d phi is f dB, in other words. That's how you connect the two. Okay, so what we have from above is that f in units of the Planck scale is coming out in this simple single scale situation as 1 over L squared. And so this was for the B field. If you take, say, a Ramon-Ramon field, you can, of course, do the same thing. So, for example, for the corresponding Ramon-Ramon field in theories that have a 2 form, just the same analysis gives a similarly suppressed answer, suppressed at weak coupling and or large radius. So that's going to be important in the next step. So here we saw that at this level of analysis, with very non-generic choices of sources in the background, but for this case, you get contributions to the action, including the potential term generically, which have this periodic dependence on the axion B. And so it's really, up to 2 pi's, it's like this. So B, there's a periodicity under B goes to B plus 2 pi, depending on your conventions, but it's something over order 1. So an example of such a function would be, some sinusoidal function, which would be a function of B, plus some phase if you want, and written in terms of the canonical field, which is usually easiest to work with. That's this ratio of the canonical field divided by its f, the so-called axion decay constant. Okay, so this is the structure that you get for axions that descend from string theory, where you include non-perturbative instanton contributions to the potential, which depend periodic sinusoidally on the axion. And this pattern of this small ratio between the period in canonical units and the Planck scale is not just an artifact of this very simple example that I wanted to show you explicitly. At the level of a single axion, I won't say it's a theorem, but it's been scanned over in, so this is happening for a rather simple reason here, as you can see, and there are no exceptions known, despite many papers really mapping it out. These days, people are thinking a lot about how much more general things get with many axions altogether. But let me stick mostly to single field and maybe make comments about those things later. Let me next explain why this is interesting for inflation. And gives a place where the string theoretic version of axions really is more optimized for inflation than this traditional field theory version, for a very simple reason. At least, well, that is within string theory, the generic case is more optimized for inflation than the naive embedding of the traditional field theory version, I should say. So far, suppose we just stick with what I've said here, which is to say, turned off all this stuff. Then we would expect a potential of sort of this kind of form up to a phase and so on. So this is actually a scenario for inflation that was studied by a field theorist much earlier called natural inflation. And it's a nice idea. It uses the kind of shift symmetry of axions as a control factor, as a motivational control factor for an inflaton, and it gives a kind of fairly specific phenomenology as a result of this form of the potential. But you can easily check that if you want epsilon, which is m Planck squared, v prime over v squared, and eta to be small, as they need to be for inflation, then this requires f bigger than m Planck, or I shouldn't say much bigger, but sort of bigger-ish than m Planck. You can just take these derivatives and you'll see this. And so at least for a single axion in string theory, when we're under control, meaning we have large L and small g, that's not happening. So okay, so that form of inflation, single field natural inflation, does not appear in string theory, as far as we know. I mean, it's hard to be, again, I'm jealous of Leonardo. He can make these just absolute theorem statements. In string theory, it's a bit harder, but it's a very, very robust pattern that, for reasons that you can see over there, that F keeps ending up sub-Planckian. Okay, so we'll talk more and more about phenomenology of various things as we go, but let me do this kind of picture. So this model has a piece that sort of overlaps with m squared phi squared, and then it has a sort of swath of predictions for the tilt and R that depend on parameters that kind of is on this side of the famous plot. I think the latest Planck papers said they disfavor this mechanism if it's interpreted specifically enough in the sort of the same way they have m squared phi squared. But I think it's that may be a little marginal. But the point about it is that in string theory, that's not how axions work at all. I mean, for one thing, there may be many, but more importantly, each one generically couples to these fluxes we've been talking about, and if there are branes around for similar reasons, they couple directly to those. And so in string theory, generically, F is kind of beside the point. So let me get back to where I was. Okay, so as we've been discussing in string theory, in full-fledged string theory, we have these Duckelberg-like couplings that led us to these contributions to the effective potential that depend on the various moduli and directly on the Axion field. So this again was the contributions coming from these generalized flux squareds in the higher dimensional theory. Similar statements apply if there are branes around, and this theorem that there's a shift symmetry up to a discrete shift symmetry is just not true in general. And I gave you a flavor for this last time, but I'll do a specific example now, showing how, since these fluxes, which we're used to using to stabilize moduli, do so and end up depending non-trivially on the moduli, one has not just this direct dependence, but also quite generically this adjustment or flattening effect, which leads to not just this direct dependence and hence large field range, but also some funny non-analytic powers of the canonical field and the potential. So I think it might be worth spelling this out in a particular example that we worked out recently, just to give you, more of a feel for, how it really works. But are there any questions about the more big picture stuff here before I do that? Yeah. F has dimensions of mass, and again, my notation is that L is L. So L. So the length scale in this is L times the string length. Yeah. Yeah. Was that your question? Just the. Yeah. Good. Yeah. Okay. Any other? Okay. So another thing to say, I shouldn't. Damn it! I should not have called this. Let me just call this V hat. This was not the same F as over there. Okay, nobody asked me about that, so let me back up. That F was in the kinetic term. Is that clear? Is everything over there clear? The F is the underlying period of the canonical scalar field. I didn't mean to write this as F. I just meant this was a function of the other moduli. This is a term in the potential. So the potential in 4 dimensions contains these terms as we've been talking about. Okay, so it wasn't. Yeah, apologies for calling that F before. That wasn't that F. Okay, so another. So when it comes to what the eventual behavior of this is as a function of the canonical field, the relation here, where in fact, the moduli will adjust in response to the inflationary energy, will lead to some, B dependence and hence phi dependence in L, and in going to the canonical field, that will also affect the resulting shape of the potential energy. So I'll just show you all that in some example. Okay, so in kind of this pair of papers, as well as a later one, particularly this later one. We kind of wrote down probably the simplest versions of this, so these aren't the earliest, but they are probably the simplest. And it's based on compactification on a product of Riemann surfaces, which is a simple scenario for moduli stabilization that kind of, I think, is comfortably in the middle of all the extreme possibilities that one can consider there. So it's a fun example. So I'm just going to give you a flavor for it. There's a product of Riemann surfaces and some other ingredients, and there are a bunch of moduli, including the complex moduli that I mentioned last time, and those are stabilized by flux, generalized flux in general. There's the volume, which I'll call curly V, and there's another combination of the volume of the. Basically, there's the string coupling as well. There's some other combination that. There are these scalar fields, and what I'm going to write down now is the potential after we've solidly stabilized one combination of two combinations of these guys. Everything but one, the volume will be left over here. So after doing that job, I'm going to write down the potential. Let me actually write these up here. Okay, where this constant CH depends on the genus, some 7-brane number, and basically an O3 number that comes from this triple intersection of 7 branes that I mentioned last time gives objects that behave like O3s along with anti-partners. So it's a small number that appears in this construction for the reason that Leonardo had asked about last time. And actually, let me write this part up here. So we can, and that combination of the curvature, these orientifold-like objects, and the fluxes stabilize the complex moduli and basically the dilaton or the lower dimensional dilaton, leaving the volume. And so this right here is a potential for the axion B, and one of the final modulus that we need to stabilize the volume V. Okay, so this is just going to give you a more of a concrete flavor for how these specific examples work, just to make sure that we think of them as kind of proofs of principle of the more general idea. Okay, so well, here you can see, if you grant me this, which you can find explicitly in these papers, that the generalized flux here is going to help stabilize the volume in a kind of x plus 1 over x sort of structure, and you can easily solve for it. So you find this relation. So here I'm taking, there are these two terms I've written, I'm taking this one to dominate. So this is much bigger than that one for this purpose. Okay, so let's so we can plug that in to the potential term, but also we need to go to the canonical field using the kinetic term. So that goes like, because this is a simple product manifold with a single scale, we can just use our result over there, translate it between L and the volume. And you can see from the above stabilization that this is the relation that we get. Okay, so this is the way to translate to the canonical field phi, and you can solve this equation, and you get that phi is proportional to b to the 3/2. Meanwhile, up there, if we plug in v to the 2/3 goes like b inverse, we get a potential that's linear in b up there, right? So the potential goes like b, which goes like phi to the 2/3 at large phi, at where q1b is bigger than q3. Okay. Near b equals 0, it's analytic and just a phi squared. But for this combination of reasons, we get this funny behavior at large field. Okay, so this is just a specific example of the kind of thing I've been trying to explain to you generally. And once again, let me just comment that the fact that this is not phi squared, that this is phi to the p less than 2, despite the b squared there, is trivial here in this algebra, and it's just the adjustment of massive fields that are much heavier than the Hubble of this inflationary model. And I commented on the first day that it's very easy for additional sectors, even heavy ones, even Planck's suppressed contributions, to affect inflation, in a strong way. And this is an example. So when it comes to the phenomenology that I was kind of sketching over here, these powers go down in this direction. I may have drawn this somewhat exaggerated, but these string theoretic versions of m squared phi squared / natural inflation, which is known as Axion monodromy, is viable still, but only because of this flattening effect, only because of the adjustment of the heavy field. By the way, if you take a scenario like this and you just proliferate the number of fields, what basically happens is the predictions move this way in terms of the tilt, and the reason for that is that is that basically that with many fields, each one is participating and can live on the steeper part of the potential. So in terms of the slow roll parameters, so we're getting these flattened potentials, and just like in I think Leonardo already said this as well, the slow roll parameters get better and better as you go out to larger and larger field range. It doesn't get worse, it gets better. And conversely, if you have many fields, they can live on the steeper part, which is the closer part of the potential, and that drives the tilt in this direction. Okay, so are there any questions so far? Yeah. These are flux quantum numbers, so these terms come from these generalized fluxes squared that I keep talking about, reduced to 4 dimensions. In this specific model, these are fluxes that behave effectively like one-form fluxes on each Riemann surface. You can find the details of the model in these papers, but so what they come from the generalized flux squares. Okay. Yes. Right. No. Okay. So we get a potential for the field. This is how it behaves up to some coefficient. And in the same way we talked about earlier for slow roll inflation and specifically large field inflation, this gives inflation. The reason that it gives inflation is the monodromy effect, which is basically the direct dependence on B that we have in the action. So I can make the terminology a little more clear if it's not. So to me, this is a huge example of how string theory is just very clever. It knows what to do with the question of how large field inflation could work. The underlying period is sub-Planckian, but the reason for the term monodromy is basically the following. So we have this kind of structure. And so we work on, we get a potential for the inflaton from this, solving the equations of motion for all the fields in a way like I described here. And that gives, on each, so for a given choice of these Q's, you have a potential that may start out quadratic, as this one does near the origin, but it flattens out for a very simple reason. But then you could have shifted B by its underlying period and adjusted for that with a shift in the Q's. Okay, and what that means is there's a branch structure. So the whole theory has a periodicity, which I'm drawing badly. Has a periodicity of the naive amount b to b plus 2 pi or whatever that traditional axions would have, but on each branch of this potential, the field range goes on forever. So the whole theory still has this discrete shift symmetry, but it's not operative on a given branch of the potential. So if you go around, the underlying period once, again, you could adjust for that with these Q's, and that readjustment is basically monodromy. Yeah.
So because the data raising will stay on a branch or everything, because it's some dual frame, you can do that. So every time you go around, something else is like stretching.
Well, there is a dual, yeah. I mean, yeah. So exactly. So some charge is building. So there is a version of this which has a dual description, as was just alluded to, which is, I've said all these fancy things, but the basic mechanism is, as was just said, the following. So consider, say, two space-filling branes, like these circles, on a cylinder, okay? So if you move one relative to the other, it's periodic. If instead you stretch some brane between them, now moving it around relative to the other one is not periodic. It's just as simple as that. I mean, it's really the dumbest thing. And
That
this version, or this particular example gives a potential that is linear in the field, and is in fact dual. In fact, the realization of it that we have is in a dual description where it comes from the related from the fact that there's also direct dependence on B in brane actions. So the branes in string theory also typically depend directly on the axions, and so if you have in this messy extra-dimensional compactification, if you have branes around wrapping cycles and so on, then typically their contribution to the potential depends directly on the axions as well. I was going to cover that, but I'm not sure. Yeah, good question. Uh-huh. Say again? Well, let's see. What were we doing? So this piece here is coming from different components of F, specifically F3 tilde squared. In the 5 form, there's a contribution that depends directly on the C2 axion. Yeah, but in this particular model, that was stabilized at its origin. Yeah, but yeah, that would have appeared here. And actually, I mean, in fact, in that paper, we have a collection of examples, some of which use the generalized flux of that piece. So just for the record, the P's that have been realized in this kind of way are the following. I don't think there's anything that fundamental about this list, but yeah, okay. Okay, so it's also a really fun thing how brane actions depend directly on axions as well. It's a T-dual of this, so maybe I'll just. Unless anyone wants to see it written in terms of the B's and C's and stuff, I will. Maybe you can agree just based on this picture that such things such dependence will be generic for branes. It's also a consequence of the ADS-CFT duality, where, after all, Ramon fluxes become traded for D branes, and so the dependence on B that there is due to the fluxes becomes the dependence that there is in the brane. Okay, so this mechanism has been studied from all these dual points of view as well. I want to make it very clear, but I also want to get a chance to list some of the others. Okay, but let me sorry, I had yeah, let me just say a few more words about the phenomenology and what's being done now, and then move to a quick description of some other mechanisms that are interesting, so you get a bigger picture. So, is everyone clear on the basic structure here? Is there any questions? Okay, so as you can see, then the pattern that's coming out is that the potential, well, it's some phi to the p, mu to the 4 minus p, and these, specific enough examples, that's what's coming out. Generally, some flattened v naught of phi, let's say. Then there will be these instanton type effects that I mentioned. Furthermore, F will depend a bit on phi. And furthermore, there's other periodic effects. So, for example, there can be periodic, at some level, there's periodic particle or string production here. Which happens because this structure applies not only to the space-filling fluxes and or branes that generate the potential, But that structure up there applies also to higher codimension wrapped objects. So in this same picture, we were thinking about these endpoints and the wrapped brain as being space filling, as filling all 4 dimensions and producing a contribution to the 4-dimensional potential. But the same picture, since I didn't draw the 4 dimensions at all, would describe also, so this applies also for, non-space filling brains. And in the Axion description that I've focused on mostly, there's a dual description of that which reflects this. Okay, so I'll just appeal to this wind-up toy, since it is faithful. Okay, so that means that there's the underlying potential that just keeps growing, but each time around, depending on how far apart they are in this direction, there will be some degrees of freedom that whose mass depends on where you are in the rotation, right? And the brain that becomes light, so the whole spectrum is invariant, but a given brain just keeps getting heavier as you go more and more around. Okay, so the whole spectrum is invariant. So as you come around, the spectrum comes back to itself, but individual members of that spectrum just keep building up energy. So that's what monodromy means. And it appears all over the place in string theory and supersymmetric field theories and so on. Okay, so because of that, there's physics that reflects this underlying periodicity going on, which includes, again, instantons, but also potentially, depending on the parameters, particle or string production every time around, because of the dependence of the masses and tensions of these guys on phi. Okay, so each of these things. So this gives predictions for R, which is robust. It's in fact in a nice place right now. And NS, which is a bit fungible because of the multi-field thing. But that's interesting enough, but it's 2 numbers, and although R, as I've argued before, is as interesting as, so it's 1 number, but like the cosmological constant, it would be super interesting just as a number. But anyway, the rest of this stuff gives the possibility of some much more detailed phenomenology, which could be just undetectably small, but because the data is there and there's some ranges of parameters where this would be interesting, it's an ongoing effort to search for that and constrain the parameters of that. And it's a lot of fun, and in particular, this periodic particle production aspect of it still needs some theoretical work to lay out properly. So that's one of the things we're trying to do, and it in fact generates a non-Gaussian signal that's quite interesting, as Leonardo and I are playing with these days. I could explain more about that if people want, kind of coupled to Leonardo's lecture today on the non-Gaussianities, but let me leave that for now, unless there's questions, and at least kind of mention a few more mechanisms. One of the just to labor this a little bit longer. So these kinds of things can give predictions for both extra structure in the 2-point function and the higher point functions that Leonardo was calculating for you today, in a way that gives detailed shapes for these things. And it's a little bit nerve-wracking because even if some theorist has the right idea for such an extra feature or structure that could be in these observables, it's very easy for the signal to be lost, because you need to have the right functional form in order for it not to wash out in some data analysis that searches for it. So so you can quantify that, and but it's a lot of fun to think about it, and I'm just saying it's one of the roles of actual models and mechanisms, say from the UV, that perhaps goes a little bit beyond the effective field theory story, which I think is great, is just that. I mean, in Leonardo's, as he explained, he had these various coefficients that could depend in general on T, and you can, restrict to certain symmetry classes and get a lot of mileage out of that, as he explained. But, if there is, I mean, this is just an example of how such a thing could work. If there is a structure that's there that would give, more detailed information about UV physics, it's really, just as a practical thing, it's not enough to just look for any function of T or any function of the non-Gaussianity. You're guaranteed to find it, but it would be statistically insignificant if you just allow arbitrary numbers of parameters. So there's an opportunity with the current data to, get straight at least some further examples of, theoretically well-defined and, sufficiently precise and constrained shapes that one can, search for it in the data without adding so many parameters that, the improvement of fit could never be interesting. So it just happened. Yeah. So right now that's one of the things to do with the remaining CMB data. Okay. Are there any more questions about that? Okay. So I spent quite a while, partly because the school has been great and very broad, but as such there were, I guess, no previous lectures on string compactification, and as such it took us a while to get to even one mechanism for inflation, which I've now finally explained. And there are quite a few others that have been developed, some in a lot of detail. Probably the first one to mention that was a pioneering work in the field was, the upgrade of KKLT to inflationary cosmology, adding McAllister and Maldacena. And so it's basically KKLT, which I sketched for you the other day, plus an additional D3 and anti-D3 brane pair to make a nice inflationary scenario. So you have some manifold with a warped region, some confining theory in the ADS-CFT language, let's say, at the infrared end of which you put an anti-D3 brane, and also this. Then, as I said, you add another 3 brane. You have to do that, or something equivalent, to get Gauss's law right. And this sector can provide an interesting scenario for inflation, which naively would have a potential that is basically the Coulomb force in the warped geometry. So in the same kind of notation I had before, let's say this is the radial coordinate r of that warped throat, analogous to ADS, basically, but some confining geometry. And so it's basically if you just consider the interaction energy between the 3 brane and anti-3 brane without just one contribution to it, I should say, you get basically the Coulomb force in this kind of 3 brane setup, the 1 over r to the 4th that you're probably used to from ADS-CFT. However, and one of the great things again about this paper is that it really put the field on much more solid footing by being careful about the need to control all of these higher dimension operators. This model is a small field model. At the end of the day, it's kind of one version of it at least is kind of an inflection point where there's a presumed accidental cancellation of the many contributions to the potential and its slow roll parameters that give a small region of inflation. And these guys emphasize that although this is the naive answer, the true answer would be sensitive to quite a number of additional operators that would be generated from the physics of the whole thing. So, in the Axion story, there's this underlying symmetry that helps a lot. Here, one is only interested in small fields, so you can easily imagine an accidental cancellation among all these contributions, which could produce a step like this. And in a large number of works, people have laid this out, partly using ADS-CFT technology in a nice way, and given kind of a statistical treatment of how this might work. Okay, so it is one of these examples where epsilon is much smaller than eta, where hence R is unobservably small. There's an interesting possibility, not just here, but probably in other cases as well, that actually Joe laid out very nicely, and Henry Tai and others, of a possibility of cosmic strings from the exit. Basically, depending on the details, there's a stringy version of a Kibble type mechanism that can happen when these. So the potential is coming from the motion of the three brane, as I said, in this region. The end of inflation, I should have said, is very pretty. It's the three brane annihilates with the anti-three brane, and that's the end of inflation. So the whole sector just disappears when it's done its job. And because of the low energy in the gravitationally redshifted warped region, turns out that cosmic strings are viable in a way that they would not have been otherwise. And that's something that can still be looked for as well. There's been nice treatments of this, given the many contributions, using interesting ideas of random matrix theory to try and when you have a system with many degrees of freedom, you can make sort of educated guesses about how they might behave statistically, and that's given an interesting view of that subject. So I would recommend, I've said it before, but I would recommend the book by Bauman and McAllister for the latest on that, and an overview of many more ideas. Another one, which was brought up earlier in the lectures, was let's say there's a class of ideas that involve first of all, picking a Calabi-Yau manifold and taking the so-called Kähler moduli, which are the sizes of 2 and 4 cycles. The overall volume can be boiled down to one of these, and then there are others. Trying to get those to behave as inflatons, and this has been done in a specific scenario for moduli stabilization, which is called the large volume mechanism, which is a sort of generalization of KKLT in a certain regime. So there's the superpotential that we talked about before, with some flux term and some non-perturbative contributions that I briefly, I think, mentioned came from instantons. One way they come about is from instantonic D3 branes. And that's what we had in KKLT. But what these guys do in a different way is take the the Kähler potential and include some alpha prime correction, which gives a 1 over volume effect. So this is this is some computed alpha prime correction. Use that as one of the contributions that is a leading order effect in stabilizing the moduli. So I'm trying to give you the essence of it in order to get to the inflationary. Okay, so evidently this leading alpha prime correction depends, as I've written it, specifically on the volume, whereas there are in general multiple Kähler moduli, only one of which is the volume. And the idea is to separate them into two classes. So here I've included these instanton effects, coming from these D3 branes, which are wrapped on all the various types of force cycles. And the idea is for most of these, so aside from the volume, from the sort of rho that's associated with the volume, rho in my other language is like L to the fourth, so it's like volume to the 2/3 as we had before. Anyway, aside from that one, the others, or some of them, are taken to be logarithmic in the volume. So you look for a solution where the other rho I, I'll just call them rho small, are taken, you look for a solution where they scale logarithmically with where you want the volume to get stabilized. And then what that does is allows these terms, which are exponential, to compete with some power law term there. Okay. But there's then this exponential relation between the volume. So the volume is exponentially larger than the sizes of these other cycles. Okay, so that's why it's called the large volume scenario. Anyway, there's a lot more to say about this, but basically, if you take some specific examples of this and take one of these rho smalls as your candidate inflaton, because in this scenario you treat the volume first and the other stuff is relatively unstabilized and flat comparatively, so those become candidate inflaton fields. Okay, and long story short, if you do that and you include some plausible, not only that first alpha prime effects, but some plausible loop effect, you get at least a toy model for a potential, in the sense that it's pretty subtle to include some alpha prime and some loop effects and not others, but there are arguments about this. Anyway, at some level of analysis, you get a pretty interesting form of the potential, which has this structure, and it's interesting because it's a potential string theoretic version of something like this old Starobinsky type model, which is also currently viable once again. Okay, so there's a lot of different possibilities for inflation in string theory. I could go on. Maybe I'll mention. I think maybe I'll just I'll mention one more and then draw a sort of diagram that I kind of like to do. So at the beginning, so let me kind of, so there's these various observables, and there's kind of a distinction we talked about originally between large and small field inflation. So, there's small field inflation that, let's say, is very Gaussian, so small field slow roll, among which there's this warped D3 brane inflation, this KKL-MMT. There's this sort of fiber inflation. That's what this thing is called, I should have said. So this is called fiber inflation. And so that, let me kind of draw it down here. It's maybe getting toward large field, but it's still pretty, it's like an R of 10 to the minus 3 or something. Then there are these, okay, and then for larger R, there's this Axion monodromy class. And then for, non-slow roll, there's mechanisms that apply on a steep potential. So, and these are non-Gaussian, like the DBI, and also something which we developed with Leonardo and others called trapped inflation, where one works in the regime of Axion monodromy, in which the particle production becomes such a strong effect that it slows the field down on a steep potential and gives strong non-Gaussianities of the kind of equilateral shape that Leonardo discussed. What I said we're doing now is working down here, including residual effects of particle production. But there's kind of interesting relations between all these possibilities. So trapped is just a word for phi dumping energy into, so dumping energy, and particularly kinetic energy, dumping its phi dot into some extra degrees of freedom, like in the phi squared chi-squared type coupling that I discussed earlier in the lectures, where if phi is rolling time dependently, chi can get produced. And in this string theoretic structure with the underlying periodicity, if that happens once, it keeps happening, and that's why it can be a non-diluting mechanism for giving inflation on a steep potential. So this works at weak coupling, and it's kind of the weak coupling analog of this DBI mechanism, in which at large n we get motion on the Coulomb branch of, say, the n equals 4 theory, which is limited by the speed limit in that dual geometry. So these guys are related by changing parameters. This trapped inflation is related to Axion monodromy by changing the level of particle production in the process. And this KKLMT is related to DBI via basically the steepness of the potential, and therefore how much the DBI part of the action matters. So, and then there's this class involving Kähler moduli. Sometimes people fold in Axion partners of those. And so it's a not anywhere near, in string theory we don't have anything like the, you can't just say, oh, it's one field and we're done. It's very complicated, but at the same time, as I've tried to explain, there are mechanisms for inflation which are, quite robust in themselves. They have a certain simplicity, each of them in itself. They can be distinguished by the data that is collected and being collected in an amazing way. I mean, it's just a true fact that we are doing science with string theory in the traditional sense. Okay, so I just wanted to sum up and make a few more comments. But are there any questions about the details or the very brief survey of other possibilities that I've given here? Okay, good. So okay, good. Thank you for asking, and I know you've worked on this, so I should have been more. So I briefly alluded to the multiplicity of axions that there can be, and once you proliferate the number of axions, as you know very well, that can relax. Even if you didn't incorporate the monodromy effect, you can get effectively large F axions. And it's just a matter of putting in all of the. So I kind of wrote this general mixed kinetic term coming from the higher dimensional kinetic term. There's the possibility of there's another matrix inside the. I don't know what notation to use, but there's some matrix of F's inside this cosine term. So there's some linear combinations inside here. And if you include all of the mixings that there are in the presence of multiple axions, it appears that one can obtain viable inflation in that way, although there's a debate raging in the literature these days about whether there's some fundamental constraint on that based on this notion of a weak gravity conjecture, which has to do with the extent to which black holes need to be able to decay. And that, under a sort of T-duality, relates to instanton actions that contribute to axion potentials. And so I didn't dwell on that here, partly because this debate continues to rage on the internet, but I think that it's, to me, I think it's pretty clear that it's not a overwhelmingly strong constraint. So indeed, there are other examples, very plausibly, with multiple axions. One interesting thing is, I don't know of any that don't involve axions, but that may be lack of imagination. Another interesting thing, by the way, though, is in this NSR plot, this being one, those multi-field natural inflation scenarios, because they're multi-field, I think they typically move this way in S, whereas the axion monodromy is going in this way, so they're kind of phenomenologically distinct, and that's interesting. And it certainly would have been nice if there were some fundamental reason that one class or another can't be realized. But I think that's a bit too strong. Any other questions? Okay, so let me just make some final comments. I've tried to, the details are very interesting, but also just the big picture again. One thing I've tried to get across is the subject of cosmology. If this is a formal TASI, so to speak, so let me come back to the motivation for it. To me, it's just kind of a no-brainer, because the formal questions in the subject are as interesting as any we talk about in any part of, string theory or field theory, et cetera. They're just interesting. These structures are interesting. There's questions of the symmetry structure, how holography works, horizon physics, which I didn't get to. There's super interesting questions there. I think it's much more UV sensitive than had been appreciated. So there's all that, interesting formal conceptual stuff, but at the same time, there's this connection to data, which is a very, very precious thing. So I think it's a very special time, and thanks. Yeah.
So, with the KKL
Yes.
Where are you given? Because basically you say that you need to extend the KKL construction, including free and anti-free brains, in order to achieve the inflationary potential. And usually these brains basically are feeding the θ1 dimensions of our user theory. So we'd better not be neither on the free nor on the anti-free.
Yeah, we're somewhere else, and then there's reheating into us. There's a whole, there's so much more that we could.
Usually you need to do a bus in one throat and the inflation in another throat.
I thought the conditions weren't that stringent for reheating. Like you can do it with pretty weak couplings, but I could.
Also, we could live on D7 that kind of move near the pro.
Yeah, you thought about this. Yeah.
I was really interested in what models that possible.
Right, and that, by the way, for that, really didn't. You happen to study it here, but it would sort of be a possibility in any example, perhaps involving warping that's strong enough, right? It really doesn't have anything to do with.
What the distinctive thing about cosmic strings is they appear when one disappears.
Yeah, right.
So if you have a situation where the group is being broken or has someone here,
Right. Right. I should say also, it's not. I didn't mean to imply that this is the only way to do inflation in KKLT. Of course, there are many ways. These axions appear in those models as well, and can be.
No,
but
I was just wondering, like basically during the exit of inflation is where the signal occurs, and you say that basically corresponds in this picture to the kind of like intuitive notion of the D3 brain and the anti-D3 brain annihilating.
Yeah.
Then it comes like basically the reheating comes as the natural energy input due to the annihilation, right? But basically I was wondering, like basically in the compactified space we need to be near enough to all
Yeah. No, this is you need to be morally near enough, so coupled strongly enough.
So
Yeah.
that we can get the effect of reheating.
Right.
But not in the region itself, because otherwise we cannot be in the brains itself, because otherwise we would
you
be
can have more
annihilated.
D3. You can have 7 D3s and 1 D3 part.
Okay, and then
Yeah, you could be quite close, and you don't really come about till later, so it's not.
right.
Yeah. Right, and of course, cosmologists have thought about that for much longer, and it's in that context that I'm pretty sure, it's of course there are constraints, but the coupling, doesn't have to be. I mean, the coupling can be pretty weak and still get good reheating, depending on the details. But it's a good question. There's work on other interesting things that can happen during the reheating phase. Although it's very hard to access observationally, there are interesting field theoretic phenomena that can happen. These oscillons, and there's a whole other story with that. So it's a good question. Any other?
Thank you again. Could you use the plane, the U1 triple verse that you were showing, and then just wrap that up on an S1, and then just have that be an Axion?
Well, yeah, people have thought about that kind of sort of effective field theory realization. I don't think there's anything wrong with it.